So I'm Jean-Michel Fried. I'm from a French National Research Center in FEMTO-ST in Besançon, and I'll be talking about hacking radio frequency spectrum. Basically, I want to introduce you to a few basics about GNU Radio, and actually not only GNU Radio as a radio frequency signal processing tool, but basically as a more general framework for getting familiar with digital signal processing and data acquisition. And I really think that it's a nice environment for not only research, but training, education. That's a little bit what I want to show you, that actually GNU Radio is much more than just signal processing. But the first question we might ask is, why are we going for digital? I mean, analog radio has been around for ages, and what are the point of getting into digital software? So basically, people started thinking, if you look at the reference in the literature, of going from analog to digital hardware at the end of the 50s, basically at the beginning of Apollo program. Apollo was the first airborne system with a fully digital IMU. Before this, the Polaris missile from the Navy were switching from analog to digital IMU. And the reason why in the beginning of the 60s, people decided to go from analog to digital signal processing, I've summed up the three reasons here, is that you have flexibility. Basically, you build your hardware once, and you can just tune whatever algorithm you want on this hardware. So you just bother once with manufacturing the system. Reconfigurability means that once you have designed your system, you can change parameters as your missile or your plane is flying. In my case, when you switch on an atomic clock, you want a startup phase, and then you want a running phase, and these parameters might not be the same. So reconfigurability means that you can change the parameters, which you can hardly do with analog feedback control. And finally, reproducibility means that your analog components are not going to age over time. If you have a capacitor or resistor-based feedback control, these components are going to age. The value of these components are going to change with temperature or with capacitance or with moisture levels. This is not going to happen with digital hardware. Digital hardware will always make the same computation. Same input means same output. So reproducibility is really an important aspect because you can predict how accurate your calculation will be. So basically, the paradigm since basically end of the 60s is to a bit shift from hardware to software in general. And I want to show you in this particular case of radio frequency signal how this paradigm change is now reaching the general public. Now, you should be aware that I'm not going to claim that digital processing can do everything that analog processing can do. There is still a lot of fields where only analog processing can go, and basically baseband radio frequency signal processing can only be done using analog hardware like acoustic wave filters, correlators. These are things that nowadays digital chips available to the general public will not perform multi-giga sample per second operations. These are still limited to analog components, but I want to show you nevertheless that there are quite a few things that we can do. Now, I've been very much inspired by a website by people who have written a book about GPS and Galileo, digital-based global navigation satellite system receivers, people from Denmark, I believe. And what they have on their webpage is this view graph, where they explain that originally the hardware receiver the radio frequency receiver was hardware. That's your old 70s and 80s radio frequency receiver where you would have AM, FM demodulator, and if you wanted to go for digital or another mode, basically you just have to change and buy a new radio. The dream of software-defined radio is to get rid of all this hardware, all this dedicated hardware. Now, at some point, you still have an analog signal which is flying over the ether, which is radio frequency wave. And the first step you want to get is analog to digital conversion to convert this radio frequency signal into an analog signal that's going to be processed, and everything you want to be in software. Now, nowadays, with current A to D converters, which can run easily up to a few hundred megasample per second, this is something that you will do in the HF band. So let's say in the 0 to 30 megahertz band, this dream has become true. You can sample baseband a 30 megahertz signal and basically process the whole band. In UHF, VHF, so 30 megahertz up to 3 gigahertz, this is just physically impossible. nowadays, general purpose A to D converters just don't have a bandwidth for baseband processing at such a high frequency range. So what we're going to actually use in the real world is a mix of a limited hardware front end where your low noise amplifier and mixer is going to something I will be defining in the next slide. So basically, you want a very basic hardware, general purpose hardware, which is not going to limit your capability to process data, but once you have moved your signal from a baseband frequency to a frequency range or sample rate that is manageable by software, then you're going to process everything by software. So nowadays, we're at this stage, and what I'm going to show you is that you can get such hardware for a very reasonable price. Just to make sure that everyone is on the same basic, I'm sorry for people who are doing signal processing, I'm sorry from radio amateur, this is already obvious for you, but just to make sure that everyone is clear about things, the crucial part of this mixing part about frequency transposition is the mixer. So let me just remind you a core aspect of radio frequency signal processing, which is this mixing component here, which takes a radio frequency input, a local oscillator input, so these are two sine waves, and we're going to generate an intermediate frequency. And the core mathematical relationship is that if you have a product, so a nonlinear function, a product of two cosine functions, you will generate the subtraction and the addition of these two attributes. And if you do this, not with constant values, but with sine waves, so cosine of a first frequency times cosine of a second frequency, what you see here is that you're going to get the subtraction of these two sine waves and a frequency and the addition. So basically, by having two frequencies, F1 and F2, if you run a local oscillator, F1, a frequency, radio frequency, F2, you're going to generate two signals, F1, F2 minus F1 and F2 plus F1. And if you do this with F1 close to F2, if you bring F1 close to F2, you're going to generate two sine waves, one which is very high frequency, which we're going to get rid of by low-pass filtering, and one which is close to the carrier. And if you have an A to D converter with a low bandwidth, low meaning something like in the 100 megahertz range or tens of megahertz range, then you can have a low-pass filter which is going to get rid of all these arrays, and you only keep your F1 minus F2, and this is what is called frequency transposition, and this is what the mixer is doing. And this aspect of signal processing is actually what is used in the hardware I want to discuss with you today, which is digital video broadcast receivers. There's been a lot of fuss, and I should really emphasize that I'm certainly not the best person here to talk to you about this, because I've not been a developer about this project. I've just downloaded the source code on the website and been using it. But there's been a lot of fuss for the last 2.5 years about these digital video broadcast TV receivers, which are sold on the web, actually, that are sold simply for about 25, 30 euros. And what I want to show you here is that for 30 euro, you can get introduced to radio frequency reception using the GNURadio environments. So I'm not going to give you any trend of one of these DVB receivers. The only thing that you have to look at is the chipset these supported by these digital video broadcast receivers. So you have one chipset, which is analog front end, which is this frequency transposition I just mentioned to you, which is basically two mixers. You have your radio frequency signal, which is what you want to measure. You have a local oscillator, which is something that's tunable, software tunable. And this local oscillator will allow you to bring your radio frequency signal into the frequency band that is accessible to the A to D converter, which is included in the Realtek RTL2832. Now, the hardware properties of this RTL2832 is that it's 2.8 megahertz bandwidth. So your sampling rate is about 3 megabit per second, 3 megahertz. And you must bring your local oscillator within 3 megahertz of your radio frequency signal in order to be able to process it. So this is the basic core aspect of zero intermediate frequency, zero IF receivers, where you just take a radio frequency signal, transpose it into a frequency band which is accessible to A to D converter by mixing and low-pass filtering. And because a radio frequency signal is defined by two quantities, its magnitude and its phase, you cannot just make a single mixing step, because otherwise, if you have just a sign of the difference of your two frequencies, if a phase between the two signals happens to be 0, then your sine will always be 0. So you need the two components, the quadrature component and the identity components, where you mix by two phase-shifted versions of a local oscillator by 90 degrees. This is all very well known for radio frequency signal processing people, and this is what is included in hardware in these components. That was just the basic introduction about digital video broadcast receiver processing for software-defined radio. So this chip here, which I should just bear with me for a second. Yeah. So what I'm talking to you about is this little chip here. So these dongles that you're going to buy for about 25 euros, they give you the basic information about the basic hardware for getting introduced to software-defined radio. And the environment for running this hardware will be GNURadio. So what is GNURadio? GNURadio is actually a framework which allows you to assemble various signal processing blocks. So you have three main blocks. You have obviously the input. The signal input is what signal you're going to feed. So the digital video broadcast dongle is one possible source of signal. The sound card is another one. I'm going to give you an example of how to use the sound card as a signal processing input. And you've got a whole range of hardware which is sold by a company called Ethos Research, which are the Universal Software Radio Peripheral, USRP. You have a whole range of hardware which costs about 500 to 600 euros. So depending on how motivated you are, you can get started with your sound card, which doesn't cost anything because you all have them on your computer. You keep on going with your digital video broadcast receiver like this one, and at the end of the day, you just, if you're really interested, you buy one of these USRP with an increase about tenfold of bandwidth in each case. So you go from 100 kilohertz to about 3 megabit per second, and then you go to 64 megabit per second. So you have an improvement of a frequency band. Then you have all the processing blocks. That will be the core aspect of my discussion in the next 50 minutes or 45 minutes. And then you have the output. So an output might be a file, might be an audio stream, as we are going to see next. We can just listen to the radio. That's what you expect from a radio receiver. You can have an oscilloscope output. We can have a frequency synthesizer that is going to generate a radio frequency signal. So there's a whole range of things that you can do. But the basic flowchart of data processing is input, processing, and output. And these are all blocks that are provided by GNURadio. So it's really a general purpose framework. Basically, the message I want to get to you is that you should not limit yourself to the input and output peripherals that are provided by GNURadio, because being an open source project, you can just write your own blocks. And if the peripheral that's provided by GNURadio does not fit your needs, then just add whatever functionalities you want. It's really easy to do. Just a quick reminder about signal processing basics. You might think, hey, great, I can get a 3 megabit per second A to D converter, so why am I going to use my old sound card, which is only 96 kilohertz bandwidth? Just a quick reminder is that in order to gain 1 bit of resolution, if you want to do oversampling, so basically averaging multiple samples, you need to increase 4 times the sampling rate to gain 1 bit. 4 times because your noise level is decreased by the square root of a number of a frequency increase, and basically 1 bit multiplied by 2, square root of 4 is 2, so you need to multiply by 4 the sampling rate. And this means that if you compare the resolution of your 2.8 megabit per second dongle with the sampling rate of a sound card, you will see that the 8-bit this thing here is an 8-bit A to D converter. If you think of it by oversampling and you go back to the sampling rate of a sound card, that would mean that you only gain 2.5 bits. So what I want to tell you here is that don't take this as a high-resolution sound card, because by oversampling using an 8-bit digital video broadcast receiver, you only get 2.5 bits, and 8 plus 2.5 means you have a 10-bit sound card, which is a very crappy sound card. So if you can live with low bandwidth, high resolution, go for the sound card. If you need the bandwidth, go for the digital video broadcast receivers. It's not a matter of binary decision. It's to read what kind of objective you want to reach. Frequency range this dongle is operating in is 50 megahertz up to 2.2 gigahertz, with some holes in there, but basically 50 megahertz to 2.2 gigahertz. And then if you want to make a wideband FM receiver, again, you take your GNU Radio graphical environment, you have the source here, which is this data stream from the A to D converter. This data stream is low passed in order to decimate the data flow, because here you have 2.8 megabit per second. That's a little bit megabyte per second. That's a little bit too much for most computers, especially for my old computer. So the first thing and anyway, you don't need 2.8 megabyte per second to process wideband FM modulation, which is only 250 kilohertz wide. So the first thing you do is you take your data source, you decimate the data using a low-pass filter. So basically, you get rid of one of every 16 sample, and then you just implement the wideband FM receiver block from GNURadio, and I'll end up falling. And at the end, at the output of this receiver, you just send the output to the audio sink, and you have your sound if everything operates properly. So it's really a matter of 4-block assembly to get a wideband FM receiver. And here you have a whole list of the functions that are provided by GNURadio. So basically, you have a graphical environment, GNURadio companion, that helps you select all these blocks, these processing blocks, the sources, the sinks, synchronization blocks, digital modulation blocks. Basically, all this kind of stuff is going to help you get started with software-defined radio. And what you were supposed to do to see is I've also added on my wideband FM receiver block, I've added the Fourier transform sync graphical user interface, and the Fourier transform sync basically gives you the Fourier transform of your frequency band from 104.7 megahertz. This is 10 minutes ago what the guys from the FM radio emitter were generating, and you tune your frequency range, radio frequency gain, and you see nicely that there is only one emitter around here, and that's the guys from the FM radio emitter. So that really helps you finding where your signal source is. The beauty of digital signal processing and flexible hardware is that you can just do anything you want. So this is something I've stolen from the web, from the guy who has been doing on the repository of GNURadio project, the radio data system acquisition, the RDS system. And what you can see here is that this guy has been doing a very fancy assembly of blocks. But the end of the story is that he's able to receive the analog signals, so the sound of your broadcast, FM broadcast, and at the same time, he's receiving all these messages that you see in your car radio that tell you what kind of channel you're tuned in, what kind of program is being broadcasted. So the beauty of software-defined radio is that you're not changing anything to the hardware, you're just adding more processing blocks, and suddenly you get from basic sound card, sound or music coming out of your radio, you add the digital functionality. So this is the kind of output that you would be getting by running the RDS functionality that is provided on the GNURadio website. Now, this is all user stuff, and you're not interested, or at least I'm not interested, I believe you're not either, in just using. You're developers. You want to add your functionalities. Using is just fun for the first 10 minutes, and then you want to add your own blocks that are not available in GNURadio. And of course, GNURadio being open source, the only thing that you're encouraged to do is read the existing block source code and just modify them or add your own functionalities based on what these guys have been doing. So one example here, and what you cannot see, is that I've got my digital video broadcast dongle over here connected to the computer. I've got a modem, a radio modem. This is frequency shift keying, FSK, modulated radio modem, the kind of little thing that you buy for nothing that are going to open your car, these remote keyless entry systems. And when you switch on this modem and you feed the wideband FM receiver function of GNURadio, you see here hardly these peaks going up and down. These are bits. So basically what FSK is doing is it encodes each bit in a different frequency. And when you feed a wideband FM receiver with these varying frequencies, it's like in the analog version where your phase lock loop of the FM receiver kept on jumping from one bit to another. Here you get the digital version of the phase lock loop going at two levels, which are the two frequencies encoding the bits. And these are basically what I've written here is because I know that my radio modem here is communicating at 4,800 bits per second, I just have to sample every 1/4,800 seconds the value of this bit stream, and I can decode a stream of data. And I'm not going to spend a lot of time doing this, but these are the sentences I have been emitting. So this is what I've been programming my radio modem to send. These are the sentences that I have received using my very basic decoder, which is, again, just a threshold detection. I'm just putting a threshold here. If it's over, it's a 1. If it's below, it's a 0. And this is a very simple decoder. And what you see here is that you've got all the header of this communication. So you've got a lot of crap with an address, with a synchronization stream, this kind of stuff. And at the end, you got the message. And if you look closely at the slides, if you want to take a copy, I'll remind you at the end of the talk where you can get the slides. If you look carefully, you will find all the sentences that I have sent. You will find then again the receiver. So basically, again, with about 10 lines of code and using the GNURadio functionalities, you can write your own digital mode decoder. So what I want to introduce now to is how did I address the problem of writing my own decoding software. The way I work, I'm not saying it's the right way, I'm just saying that's my way of doing things. The way I'm doing things is I first record files of the data I want to process. So basically, these are sound files or binary files with sequences of acquisition from my dongle. This allows me to run my decoding software without having to wait for the event that I want to decode to occur. And the event I'm going to be interested in, what I'm going to show you next, is one protocol I've been interested in for a long time. It's called HackRF. HackRF is a digital protocol used by planes to communicate with airports. Basically, it's a general purpose information. It's nothing confidential. It's basically level of fuel, weight of the plane, basic information such as we have a sick passenger, or you'll see some other stuff. So HackRF is a digital protocol used in airplanes to communicate with airport. And of course, if you want to make an HackRF decoder, you need a plane to be over your place to listen to something. And that's very annoying because when you want to debug something, you don't want to wait for a plane to come. So you record a few signals, then you prototype your decoding algorithm. And being a serial processing person, I'm most familiar with MATLAB or its open source version, which is GNU Octave. If people are familiar with Python, Python has now implemented most of the MATLAB functionalities, and numerical Python and scientific Python, NumPy and SciPy. So if you're familiar with Python, Python is very nice because your blocks that you write in Python are mostly compatible with GNURadio. So you prototype first using a scripting language such as GNU Octave or Python. Then you transpose from this interpreted script into a compiled C program. And that takes some time because a single line of MATLAB can be many, many lines of C. And at the end of the day, you just wrap this C program into the GNURadio framework, which is really nothing much. This is really just copy-pasting a few lines from a basic block. So this is the flow chart that I'm thinking of, is record some data. This is offline processing using MATLAB or Octave, converting to C in order to fit the GNURadio framework, and by this you go from offline processing to inline processing and real-time processing, which is much more fun. So let me just introduce to you quickly what HackRF is about. HackRF, as all plane-related modulation protocols, modulations is amplitude modulated, being most resistant to noise. So you have AM modulated, so we are going to run our data stream through the AM demodulation block from GNURadio. And then what you learn from the web, and I've put for you here the references that I've been using for HackRF's information, you have encoding at 1,200 bits a hertz sine wave encoding a 0, 2,400 encodes a 1, and you have communication, data communication at 2,400 bits per second. So let's first think of this. That's really funny because at first time you read the manual, you're thinking, that's funny, why did they do this? They encode at 1,200, 2,400, there's a ratio of 1 to 2 here, and then they have a data rate of 2,400, which is my fastest data rate. That's really funny, why did they do this? The answer will be in the next slide. Then you know that you have a header, which is used to tune the automatic gain control of the HackRF front end, and then once you have your bits, you learn that a bit 0 means that the bit value is unchanged, and a bit of 1 means that a bit value is changed. And if someone can explain to me why people are using this funny way of encoding, I would be really interested because I don't understand it. So they don't encode the bit value, but they encode the bit change value. And at the end of the day, what I want to reach, so that you know what my final goal is to be able to, using GNURadio, to receive HackRF's sentences. HackRF sentences record 2 types of information, the flight number and the plane identity. From the plane identity, I can go on the plane spotter website and I can have a picture of a plane and who is operating the plane, which company. And from the plane, from the flight information, I go on the virtual radar website and I can check whether over my city this plane is indeed flying. So that was my purpose, to have the plane and flight information so that I can recover this information from the web. So how do you get this going? Just a quick answer, why have people done this 1,200 bits hertz encoding and 2,400? The story is very simple. If you have 1 bit here, which is encoded as either 1 full period or as a half period of the encoding signal, what you can see is that when you're going to do a convolution of this message that you're getting with either this sine wave or this sine wave, because here you have an odd function, and here you have an even function, the product of an even by an odd function will obviously have an integral which is null. And otherwise, if you have even times even, you have 1/2 as an integral, or odd times odd will give you a 1/2. So I've written for you here the 3 possible cases. You have an unknown signal, which is either one of these 2 cases. You make a convolution with these 2 functions, and you get 1/2 if you have the right version of the bit, and you have 0 otherwise. So it's a very efficient way of computing your convolution and getting the right value. So what we're going to do is going to convolve the signal that we receive from the A to D converter, and we know that convolution is very inefficient in the time domain, especially on sequential CPU. So we're going to use a frequency domain, so we will need some Fourier transform, and this is where MATLAB is most efficient. So what you get at the end of the day is you take your data stream. What you cannot see on this black and white graph is that there are 2 sets of data here. You have the 2,400 hertz bit decoding. You have a 1,200 hertz decoding. And what you would be seeing if you had this in color is that you have initially the 2,400 hertz, which is the most probable value of the bits. And then at some point, these various curves cross, meaning that one bit value is more probable than the other one. And that gives you your data stream. So basically, you will have a full stream of 1, then a 0, then a full stream of 1, and so on. So basically, getting the bit values is just a matter of convolution. Now, there is just one more trick here, is that a bit is given by a given number of samples. And the little hint I want to give you here is how the GNURadio is going to give you an asynchronous chunk of data of unknown size. So sometimes it will give you a few hundred bytes, sometimes it will give you a few thousand bytes. How do you process a Fourier transform which requires a minimum number of values to perform this operation? And what we've been doing, assume that in your buffer, in your data buffer, your Fourier transform is going to operate on a given number of samples. And at first, you only get a tiny chunk of data, not enough to make your Fourier transform. What we're doing is we are accumulating data until the full chunk of Fourier transform data has been accumulated. Then we're going to process this amount of data and provide the user with whatever result is achieved. And whatever is left, so this little chunk of data here that we have not yet processed, we're going to put it in the beginning of the buffer, and we start accumulating values again and again until we have enough data to make a new Fourier transform. So this is a little bit the trick here that we had to solve in order to, because GNURadio is not giving you a finite number of data, you never know beforehand how many data you're going to get, and you need to accumulate enough values to run your processing function. I'm not going to get into much detail about the code source. This you can find. Again, this is more for reference for you. If you want to fetch my slides on the website, which I'm going to remind you at the end of the talk, you can just fetch the data, and this is going to give you examples. So basically, in the GNURadio companion graphical interface, you have an XML file, and the XML defines what kind of input, what kind of output, so whether you have short characters, integers, floating point numbers, how many inputs, how many outputs, and you can provide parameters. So you have dynamic parameter in your blocks, and you can provide your block with dynamic parameters, not only fixed parameters in your software. So you have an XML files which define how your block behaves. You have a C implementation of your algorithm, and this is what I was saying, that going from the MATLAB implementation to the C implementation is not completely trivial, especially when you have the FFT function. You do have the FFTW library, and going from FFT in MATLAB to FFTW in C requires tweaking with normalization factor. Your threshold values are no longer the same. It does take time, but at the end of the day, you have a C function which implements your algorithm, and having done so, you have your whole processing sequence. Your processing sequence for HackRF is we first search for each data set we're accumulating. We accumulate enough data to make sure that we have a whole sentence. So a whole sentence is defined by the protocol as 300 characters. So we're going to accumulate enough data to have at most 300 characters. In these data, we're going to search for 13 periods of 2,400 Hertz sine wave just by doing a Fourier transform convolution with this signal here. If we find something that's above a given threshold, and our algorithm is very dependent on this threshold value, that's the drawback. If we find a value above threshold, we know that a message has been sent by a plane. By doing so, we know that we are going to start a convolution at the beginning of this message in order to search for the 2,400 and 1,200 Hertz sine waves, which are going to tell us whether we have bits 1 or bit 0. So we identify the most probable bit value. And having done so, we extract the bit sequence. From the bit sequence, we generate the byte sequence. As I told you before, 0 means a bit change, 1 bit means no bit change. So if you have a single error, then your whole stream is erroneous. And at the end of the day, you interpret all this data as flight number, plane identification, and so on. And at the end of the day, what you get is a whole stream of hexadecimal values which are displayed as the decoded bytes. These bytes are interpreted as sentences, and it makes your wait in airports much more playful when you are at the airport and just listening at all the sentences sent by the plane which are waiting to take off. So this is basically what I wanted to show you about HackRF decoding. GNU Radio HackRF development, you can find on the Cgran website under HackRF the implementation of this, and I hope someone wants to play with it. At the moment, it's only been validated with a DVB receiver. So this is all working pretty well, and what I would like you is to play with this software to learn how to implement your own functionalities. This is all reception. Reception is only half of a game. You also want to emit something. Emitting is really the fun part. So before emitting, the first thing I want to tell you is GNU Radio is full duplex. Full duplex means that you can receive at the same time you're emitting. And this is great fun, because if we're working with sound cards, full duplex means that you can play and receive at the same time. And if you're familiar with what this is, you can make an audio frequency network analyzer. A network analyzer is something that is going to generate a sine wave of varying frequency, and we're going to look at the response of our whatever device at this excitation signal, which is a variable sine wave. And basically what I want to show you here is that there is really nothing to do if you want to convert your computer with its sound card into an audio frequency network analyzer. You just play a sine wave. At the same time, you receive the stream. And the only little trick here is that you need to get the magnitude of a signal. And to get the magnitude, the first thing you can do is you just take a diode. So what I want to use this for is, you might all be familiar with a tuning fork. This quartz tuning fork is what you all have in your watches. This is the timing function of your watch. This is actually what you have in your watch. It's a 3 millimeter diameter, 8 millimeter long tuning fork made of quartz. When you generate a sine wave, it will start moving, and it is dimensions so that it moves at exactly 32,768 kilohertz or 2 to the 5 kilohertz. And if I take this tuning fork and I generate a sine wave at 32 kilohertz dot something, and I look at the output of a diode, what you will see here is that you see here these jumps, and this is the response of my tuning fork. So I'm sweeping the frequency range, and when my frequency is going over 32,768, I have current going through my tuning fork, and this indicates that I'm at resonance. So basically, with no equipment at all, you can make an audio frequency network analyzer. And if you really want to have nothing at all as hardware, you get rid of the diode, so the rectifying diode. And what I wanted to show you here, but it's really unreadable, is that we implemented IQ demodulation. So IQ demodulation is what I've shown you earlier. You do a mixing, but again, you do a mixing of the sine wave that is generated through the tuning fork. So you generate 32,768 hertz. You have a local oscillator, which is tuned at the same frequency as that you're emitting. And what you can see here is the magnitude of the signal going through the tuning fork. And the red curve here is the phase going through the tuning fork. So we have validated that software implementation of IQ demodulator is indeed working. And just the little trick here, and again, this is the beauty of open source, is if you stupidly do, as I did, cosine of frequency times your time, since your time is slowly drifting over time as steps are incrementing, this thing will quickly diverge, and cosine of a diverging function is not a good idea to compute. And so if you get inspiration of the implementation of a numerically controlled oscillator as done in GNURadio, you learn that at each step you increment a phase value by 2 pi times the wanted frequency divided by the sampling frequency. You normalize by 2 pi, so you keep this argument between 0 and 2 pi, and this is where you know that you can compute a cosine. So without getting into the details, again, the beauty of open source software, if I need to convince anyone about it, is that when you're doing something wrong, you can learn how people have been doing it right and just learn from your mistake and from what they're doing. So this is IQ demodulator implementation, and we've been using this for quite a few audio frequency signals. And what I'm interested in is using the tuning fork, the quarter tuning forks, as a sensor. So what's happening here is that when I'm heating my tuning fork, I can detect the frequency change, the resonance frequency change. So this is all a lot of fun, and with really no hardware at all, nothing else but a sound card and an open tuning fork. The last thing I wanted to get into, frequency counters. I'm going to skip this one. The last thing I wanted to talk to you about in the last 10 minutes is radar. I've just talked to you about emitting signals, but I'm talking to you about emitting signals in the audio frequency range, and this is a talk about GNURadio. So maybe you people would like to know how to make a radar system out of GNURadio. The most common aspect that we're all familiar with of radar is we generate short pulse, what is called pulse radar. We generate short pulses of high energy, which are going to be reflected by the target, and the target sends back a high bandwidth, meaning a very short pulse, and we need very fast hardware to sample this high bandwidth. It's feasible, of course. A lot of people do it, but it's not amateur grade. There's no way you're going to make a high bandwidth receiver for a pulse mode radar. And you have a very beautiful other approach, which is called FMCW, frequency modulated continuous wave radar. And this is what I'm going to talk to you about. And I should emphasize here, because I don't have enough space on the next slide, this is all inspired by the MIT websites. You have, again on my slides, the exact references for the last 2 years or so. MIT has been promoting a course on radar systems where they have an amazing lab description on their open course website. And really, I encourage you to go and copy what they did. It's €100 worth of equipment, and you learn how to make a 2.4 gigahertz radar. So what I want to introduce, I want to remind you how FMCW radar works. The principle of an FMCW radar is you have a voltage-controlled oscillator. That's a €20 piece of equipment. You have a voltage-controlled oscillator is an oscillator whose output frequency is defined by a tuning voltage. This voltage-controlled oscillator is going for a power amplifier because you need a bit of power, but I'm not talking about the same kind of power as earlier. Earlier, we were talking about kilowatt power. Here, we're talking about milliwatt power. This signal here is going to get through an antenna and travel over time to a target. So your oscillator here is tuned by a sine wave, a triangle wave. So this means that your voltage-controlled oscillator frequency is changing over time. What I've plotted for you here is the frequency of the voltage-controlled oscillator as a function of time. And you see that this frequency here is moving as a triangle wave. And because this voltage-controlled oscillator is moving over time, when the reflected signal from my target arrives to my receiving antenna as amplified, the mixing step here, and I remember that the mixing will make a subtraction between the received frequency and the emitted frequency. Because over this time dt, the frequency has changed a little bit, then there is going to be a bit frequency generated here. Basically, you have here an image of what the voltage-controlled oscillator was dt times before the reception of this echo. So an FMCW radar is really 3 components: a voltage-controlled oscillator, amplifiers, and a mixer. You need 3 components to make an FMCW radar, and the MIT website shows you what the component values are, and it's hundreds of euro worth of components. You have a few free parameters, but basically what you have to remember is that the only bandwidth that is needed to process FMCW radar is audio frequency signal. Even though you're measuring high bandwidth signal, I should emphasize this VCO here is a 2.4 gigahertz VCO. So this is allowed. You're allowed to emit on the 2.4 gigahertz. That's Wi-Fi, Bluetooth, all these digital modes. So this is a 2.4 gigahertz signal. But after this mixing step, you only get audio frequency bit signal. And this is really easy for you to sample using your sound card or one of these digital video broadcast receivers and process the data with GNURadio. And what I'm claiming as a novelty of my approach with respect to the MIT website is the MIT website is recording this audio frequency and post-processing in MATLAB, which is excellent for teaching. I have no problem about this. But in my case, by running the same software under GNURadio, I have real-time display of my target position. So what you cannot see on this slide is that basically this is all assembly. This is Lego-like. We had a presentation about Lego Mindstorm. Basically, radio frequency prototyping is also Lego, except that it's a bit more fancy Legos and a bit more expensive Legos. But again, this is a whole 100 euro experiment. And what I want you to see here, if you just look at this half of the graph, you have 8 peaks that you can hardly see on this projector. But these 8 peaks are the 8 targets that I've located behind my FMCW radar. And again, I want to emphasize the beauty of the GNURadio approach is that these peaks, you see them appearing in real time. You don't need to post-process and run some fancy algorithm. You just have a Fourier transform of the sound card input here, and you see these 8 peaks appear. And if I remove my targets from my FMCW radar, these peaks are just going to disappear. Let me just add that actually these peaks are not due to passive targets, but this is what is called surface acoustic wave delay lines. These are basically target simulators where the delay here is from 1 to 4 microseconds, but they are not due to targets located 150 meters away, but they are due to a specific component made of piezoelectric substrate where the time delay here is due to a tiny component here which simulates a target, which is 1 to 4 microseconds away. I've been trying to find second-hand sources of these components, and unfortunately, I don't have been able to find any cheap second-hand sources to advise you to buy from. But if you're interested in these applications, you might come and see me, and I might have a few hints as how you might be able to get some of these components. So again, at the end of the day, what does all this look like? You have these 8 peaks here from your 8 targets that are measured by the FMCW radar. And in terms of GNURadio development, it's just a few blocks that you just put together. The sine wave that generates through the audio output, the triangular wave through the audio sound card that is going to tune your VCO. And at the receiver side, you acquire what is coming out of your mixer, Fourier transform, and out of your Fourier transform, during the averaging, you see these peaks appearing. So again, the beauty of this whole thing is that you're generating a 2.4 gigahertz radar with a receiver side, which is only audio frequency bandwidth signal. So that's really beautiful. And then it brings me to my conclusion about what I wanted to show you with this GNURadio stuff. You have an open source environment which really eases the entry to software-defined radio processing. Basically, I believe that GNURadio is a beautiful environment for training, for teaching, because you just get rid of all these oscilloscopes, these function generators, without getting to these ridiculous Java-based applets where you make students believe that they're making a lab, but they're actually not doing anything because they're just clicking on buttons. With software-defined radios, you still have some hardware, but you're doing digital signal processing. You have reusable software, meaning that all these blocks that you've been writing for GNURadio will be reusable, whatever source and whatever sync you're writing. And because this is open source software, you're encouraged to add any source or sync that you might suit your needs. So that's the radio modem, that's DDS, direct digital synthesizer, all these kind of sources that are now available and which are really cheap to use. You might get started with graphical user interface, as I've shown in my presentation with GNURadio Companion. And this is all about. And actually what GNU Radio Companion is doing is generating a Python script. If you get more familiar with the whole processing chain, then you stop using the GNU Radio Companion environment and you just write your own Python programs for generating GNU Radio processing chains. And what I wanted to show you in this presentation is how I imagine that the workflow is most efficient. You record data, you process your data under MATLAB, GNU Octave, whatever scripting tool you're familiar with, convert this script into C, and wrap this C software into GNU Radio environment for inline processing. Further work, there are amazing stuff on the web, which I have unfortunately not been able to reproduce for you for today's presentation. The first thing is NOAA weather satellites. I think a lot of you people know about the low frequency 137 megahertz weather satellites, really easy to catch. Some people on the web, reference number 11 here, have shown that this digital video broadcast TV receiver can get signals from satellites 800 kilometers away. This is just amazing. I've not been able to reproduce. I can get the sound of a satellite. When I decode the sound that I receive, I don't get the image. So I'm still doing something wrong. But this is really very simple. And there's another amazing stuff from, I believe, University of Catalonia in Barcelona. These people have demonstrated raw GPS data reception. And that's really amazing because when you get the raw IQ data from GPS, you just don't get stupid timing or stupid positioning. You get the whole metrology associated with atomic clocks. Basically, you get here 5 or 6 signals from atomic clocks in space. You get geodesy, you get moisture density in the atmosphere, you get ionosphere, electron density, you get reflection on lakes. Getting this raw data is just a whole field of research open, and if you look in the geophysics field, these people have been doing amazing things with GPS data. I conclude my talk with a selected bibliography. I'm not going to get through all of this. Half of these books are encouragement for you to get into SDR. It's not technical, it's just stories about Apollo, about Voyager, about Cassini-Huygens probes. These are just stories to tell you why software-defined radio is beautiful. And at the end, there is some textbook that you cannot miss. At some point, you have to get into the maths. But when you get into the maths, because you know what you're doing and not just for an exam, it's just much more fun. If you're interested, I've written 2 papers. The English is a translation of a French article which summarizes all these documents. And if you're interested, I'll try to get in the very beginning. Just send me an email or go to my website. Website is over here, email is over here. Feel free to look for the slides on the web, and thank you for your attention.
I think we have time for a few questions. 2 more minutes. One, 2 quick questions.
Thank you for your nice presentation. About your sorry. Thank you for your nice presentation about your reception of the aircraft data thing. It reminds me very much of how in the old days computers stored their stuff on tape. And basically, that is the synchronous to the carrier frequency, the 1224 and about. You encode it, so it would be much easier, I think, to just run a phase lock loop and a zero crossing detector over it.
The fun thing about software-defined radio is that you've got so many ways of doing the same thing. And when I presented this to my friends in the lab, they had all their own opinion about what is the best way of decoding these sentences. So I'm pretty sure that the PLL would be a beautiful way of doing it, of course, yeah.
It would be less computationally expensive.
Most probably, indeed, yes.
There's a block in there that does that. There's an FSK block in GNU Radio. They'll do the whole DMOD.
Yeah, actually, let me emphasize here that what I wanted to do here was to learn how to write my own GNU Radio block. I have not emphasized this enough in this presentation, but the whole point for me was to get the AM data as a sound signal, and I wanted to write my own GNU Radio block to show people how to do it. I'm sure there are ways of doing it, and actually with the GNU Radio blocks available, you can do most things, but I wanted to learn how to new functionalities.
Question. Which hardware is available currently for GNU Radio to demodulate direct sequence spread spectrum Wi-Fi signal?
Sorry,
A normal DSS Wi-Fi signal.
you're asking me if it's available?
Which hardware is available for GNU Radio to do that?
I believe that based on the bandwidth that you will be needing to get spread spectrum analysis, only the USRP will be doing this. This dongle here is able to do GPS because it's 2.8 megahertz sampling rate, and GPS is 1.5, or GPS L1 is 1.5 megahertz wide. L2 is 10 megahertz and will not work. For Wi-Fi, I'm pretty sure that USRP will do it, but not this simple dongle. Especially because there will not, the stupid answer, because this thing will not operate on 2.4 gigahertz. It stops at 2, so only the USRP will do it.
And then do you see any problems? Because Atos was actually bought by National Instruments, I think, some time ago. So I have to probably buy a National Instruments box, or can you still buy those Atos boxes?
At least people from Atos Research have claimed on the GNU Radio mailing list that there would be no interaction or no interference from National Instruments in their selling instrument. How it's going to happen, I don't know. At the moment, I have not seen any difference. But again, I emphasize, for me, there's two very different things. GNU Radio as a framework for digital signal processing and the hardware. Atos Research is doing beautiful hardware. There is a flourishment at the moment of new boards. Whether they are equal or not, I cannot say. And if you believe Atos is not good enough, then you can just go for your own, but reuse GNU Radio framework. There's a FunCube, which is also, but the FunCube is the same hardware as this one, but with a slower, higher resolution A to D converter. So it's 96 kilohertz, but 10 or 12 bits. So again, it's a trade-off between whether you want high resolution, low frame rate, or high frame rate, low resolution. If you go on my website, jmfry.free.fr, is the first link. You will see the OVH link is the first one.
Okay, thank you. Thank you. We have to set up next.
Please let me just add one more thing. There in my lab, if you're interested in this topic, there are PhD and postdoc position funding available. Feel free to contact me if you're interested in PhD or postdoc. There are funding available. Thank you very much. So I'm Jean-Michel Fried. I'm from a French National Research Center in FEM2ST in Besançon, and I'll be talking about hacking radio frequency spectrum. Basically, I want to introduce you to a few basics about GNU Radio, and actually not only GNU Radio as a radio frequency signal processing tool, but basically as a more general framework for getting familiar with digital signal processing and data acquisition. And I really think that it's a nice environment for not only research, but training, education. That's a little bit what I want to show you, that actually GNU Radio is much more than just signal processing. But the first question we might ask is, why are we going for digital? I mean, analog radio has been around for ages, and what are the point of getting into digital software? So basically, people started thinking, if you look at the reference in the literature, of going from analog to digital hardware at the end of the 50s, basically at the beginning of Apollo program. Apollo was the first airborne system with a fully digital IMU. Before this, the Polaris missile from the Navy were switching from analog to digital IMU. And the reason nowadays, with current A to D converters, which can run easily up to a few hundred megasample per second, this is something that you will do in the HF band. So let's say in the 0 to 30 megahertz band, this dream has become true. You can sample baseband a 30 megahertz signal and basically process the whole band. In UHF, VHF, so 30 megahertz up to 3 gigahertz, this is just physically impossible. nowadays, general purpose A to D converters just don't have a bandwidth for baseband processing at such a high frequency range. So what we're going to actually use in the real world is a mix of a limited hardware front end where your low noise amplifier and mixer is going to something I will be defining in the next slide. So basically you want a very basic hardware, general purpose hardware, which is not going to limit your capability to process data, but once you have moved your signal from a baseband frequency to a frequency range or sample rate that is manageable by software, then you're going to process everything by software. So nowadays we're at this stage, and what I'm going to show you is that you can get such hardware for a very reasonable price. Just to make sure that everyone is on the same basic, I'm sorry for people who are doing signal processing, I'm sorry from radio amateur, this is already obvious for you, but just to make sure that everyone is clear about things, the crucial part of this mixing part about frequency transposition is the mixer. So let me just remind you a core aspect of radio frequency signal processing, which is this mixing component here, which takes a radio frequency input, a local oscillator input, so these are two sine waves. Digital processing can do everything that analog processing can do. There is still a lot of fields where only analog processing can go, and basically baseband radio frequency signal processing can only be done using analog hardware like acoustic wave filters, correlators. These are things that nowadays digital chips available to the general public will not perform multi-giga sample per second operations. These are still limited to analog components, but I want to show you nevertheless that there are quite a few things that you can do. Now, I've been very much inspired by a website by people who have written a book about GPS and Galileo, digital-based global navigation satellite system receivers, people from Denmark, I believe. And what they have on their webpage is this view graph, where they explain that originally the hardware receiver the radio frequency receiver was hardware. That's your old 70s and 80s radio frequency receiver where you would have AM, FM demodulator, and if you wanted to go for digital or another mode, basically you just have to change and buy a new radio. The dream of software-defined radio is to get rid of all this hardware, all this dedicated hardware. Now, at some point, you still have an analog signal which is flying over the ether, which is radio frequency wave. And the first step you want to get is analog to digital conversion to convert this radio frequency signal into an analog signal that's going to be processed, and everything you want to be in software. Why in the beginning of the 60s, people decided to go from analog to digital signal processing. I've summed up the three reasons here, is that you have flexibility. Basically, you build your hardware once, and you can just tune whatever algorithm you want on this hardware, so you just bother once with manufacturing the system. Reconfigurability means that once you have designed your system, you can change parameters as your missile or your plane is flying. In my case, when you switch on an atomic clock, you want a startup phase, and then you want a running phase, and these parameters might not be the same. So reconfigurability means that you can change the parameters, which you can hardly do with analog feedback control. And finally, reproducibility means that your analog components are not going to age over time. If you have a capacitor or resistor-based feedback control, these components are going to age. The value of these components are going to change with temperature or with capacitance or with moisture levels. This is not going to happen with digital hardware. Digital hardware will always make the same computation. Same input means same output. So reproducibility is really an important aspect because you can predict how accurate your calculation will be. So basically the paradigm since basically end of the 60s is to a bit shift from hardware to software in general, and I want to show you in this particular case of radio frequency signal how this paradigm change is now reaching the general public. Now you should be aware that I'm not going to claim that waves, and we're going to generate an intermediate frequency. And the core mathematical relationship is that if you have a product, so a nonlinear function, a product of two cosine functions, you will generate the subtraction and the addition of these two attributes. And if you do this not with constant values, but with sine waves, so cosine of a first frequency times cosine of a second frequency, what you see here is that you're going to get the subtraction of these two sine waves and a frequency and the addition. So basically by having two frequencies, F1 and F2, if you run a local oscillator F1, a frequency, radio frequency F2, you're going to generate two signals, F1, F2 minus F1 and F2 plus F1. And if you do this with F1 close to F2, if you bring F1 close to F2, you're going to generate two sine waves, one which is very high frequency, which we're going to get rid of by low-pass filtering, and one which is close to the carrier. And if you have an A to D converter with a low bandwidth, low meaning something like in the 100 megahertz range or tens of megahertz range, then you can have a low-pass filter which is going to get rid of all these arrays, and you only keep your F1 minus F2, and this is what is called frequency transposition, and this is what the mixer is doing. And this aspect of signal processing is actually what is used in the hardware I want to discuss with you today, which is digital video broadcast receivers. There's been